my friends. Hello to your favorite artist reference here, Mr. Q12. Oh yeah, from Romania. Let's see. There is no basic ADC. Here I tried to make a basic circuit, but I couldn't. So this is about some very special subject that I am not very familiar until recently, and I started to get more familiar about it. I mean, I was aware of the theory. When you read, there are a lot of YouTube videos which they are explaining the behavior and the functionality of ADC chip. By the way, ADC, it means analog to digital converter, and it's 8-bit resolution. This one, 0832 that I have in my arsenal of chips. It says there in the title as well here. And at the very, very beginning, well, I have the chips. I commanded them some years ago, I don't know, 1 or 2 years ago. And I said to myself, I will figure them out lately after I will buy them. And I buy them, and of course, they arrived, and I put them away, and I forget them for a while. And with the help of a friend, I mean, originally when I started to deal with this particular chip that I have in my arsenal, this ADC0832, I put here a very big label. I have no idea how to make it work, and I really had no idea. I tried various permutations, but this is all that I got. The idea usually is you put a potentiometer. In this case, I put a 10 kilo one, and on some of its channels, it's having only 2 channels. And I put 2 potentiometers actually of 2 kilo on both channels in this configuration that I'm having right here. I put a clock here on this line and an output. DO, it means digital output, and DE, it means digital input. And I tried various permutations, nothing works. Okay, so I went to, by the way, what it means, this digital input, what it means, digital inputs are binary inputs, 0 or 1, that are detected by the device. In simple words, any push button, switches or sensors produce compatible digital output can be connected to the digital input. Usually this is a very good explanation that I could find about it. Again, this is pretty new, at least for me, and it's not a new chip. It's a very, from what I understand, it's quite an old chip, but it's what I could put my hands on, and it was quite cheap in bulk of tens. I knew the theory, but how to actually put them to work, I had no idea. And so my friend, I talked with a friend from UK, from England, not from America. This time, only from England, and he was very good on helping me about this subject. He was curious as well because he had later, after we deciphered this thing, he told me that he had also some ADCs, but not this particular one. He had something very different. I believe 10 bits. You see, mine is 8-bit, but he had 10 bits and probably 12 bits, something else. So bigger in resolution, way more bigger than what I have here. And he made them work on his side as well. And all right, so I opened this datasheet of this particular ADC 0832, as you can see here in the title there. And actually this PDF, this datasheet is dealing with a series of ADCs, 0831, 32, this one is what I'm having, this guy here. This is my chip that I'm having. 34, so 31 here, 32 that I have, 34 and 38. These are all 4, so there are 4 chips on this page. And my 32 is not, my chip that I'm having is not really explained that well in this particular. It's like a general explanation for everything, but giving only 1 or 2 examples with one of the most popular, probably from their point of view, chips from this series. Probably 0838, they give it the most examples with, I believe. Let me check. Yeah, 0838, it was the most popular. Yeah, and 0831. But my 0832, nothing. This is also 0831, also 31 as well. 31. And I said, shit. And they are not really compatible on the pins. I believe only 2 of them are compatible. My 32 and the 31. And the 34 and 38, they are compatible between them a bit. So these are the pinouts, you see? So we are reading here. This is 38, this chip. This is 32. What I find it here usually. I was looking here all the time. Yeah. My chips that I'm having, but they have this pin configuration. They have 8 pins. But this guy, even if it says 0832, is having how many? 14 pins. And I don't have this version of the chip, even if it's the same chip. It's very weird. This one is 31, and this is something else. 34, and this is 30. So you see, they are quite different, especially my guy that I'm having here with 8 pins only. Like I said, it was quite cheap, in bulk of 10 pieces, and that's why I choose this particular one. I didn't check with the datasheet originally, in the beginning, before buying. So when I looked in the datasheet that I'm having here for this chip, okay, I get the pins, but they didn't tell me anything really. They tell me, yeah, it helped me, but not that much. And when I got to see an example circuit, nothing, absolutely nothing. How to link this motherfucker, how to make it work. And my friend from England, this is where his help came in, actually extremely good help. He stopped at this circuit here, and he told me, he sent me a message, go to this page, which is page 21, and look at that circuit that you have there, and try to figure it out by yourself, and look more closely, because this is a functional circuit, and it should work with what you have there. And when I got to it the first time, the very first time, first of all is 0838, and I completely neglected in the beginnings. And I thought it's way too complicated for my for my level of knowledge that I'm having. But after he suggested it for me to start thinking about it, I started thinking about it. And I did read the diagram. I couldn't understand much from it, especially this beginning part here, which is very, very weird. Very, very weird at that point when I was starting in the beginning. And well, I had a good idea. I said to myself, well, I should put it down in the simulator that I'm having in my Proteus. So this is probably what 74164. Yeah, exactly. 74164 is this chip here. And let's see. And this guy here, 74194. So 165. I don't remember what I did with that 165. I believe I did use it. Yeah, here it is. So I made, you see, quite a large file here. This is called ADC0832A. And I have, this is the file that I'm having here. But I have others. I have this one, I have this one, and I have this one. I have 4 of them. And they are different conception. I see. I have a reminder here that originally this was the original in the here 165. This chip. This is like an equivalent that is doing exactly the same thing, but is easier to work with, I believe. And I believe this chip my friend suggested to me to try. And we tried a lot of permutations here. We actually put 4 switches for all the Ds. You see, D0, 1, 2, 3, until we figured out it only needs these 2 bits set. This is a setting. Probably this was the very first one when we tried. Yeah, you see, this is the actual setting 0, 1, 1, 0. So this is on D0 is set to 0 through this switch here, set to 0. D1 is set to 1 here. The switch is open and it's set to positive here, as you can see. D2. This one here is set directly to 5 volts to 1, and D3, this last one, is set to 0. So this is the configuration that me and my friend, we figured it out in the with quite some effort, actually. we guessed a lot. We guessed. This is all that we did. We guessed a ton until we figured it out. Until we did see some good output. So we were checking with the output all the time, and the rest here, this circuit is part is this very complicated thing that we is having here. This diagram is having some mistakes, I believe, or some very weird conceptions that I am not very familiar with, really. As you can see, it's having a ground. You see, this is the sign of ground. This is the sign of earth. What the fuck? Why the fuck are you using the ground and the earth? Probably this is for industrial usage or of some kind, when you have to link the case, the metallic case, to the earth or something. The fuck. But it's very weird from this point of view. So pretty much the ground and the earth is the same thing. So I put the ground where the earth symbol is, even if it's looking weird. So that was also here. You see the earth. What the fuck? And yeah, it's weird. It's a bit weird. Why they use this labeling this? So pretty much the ground or 0 volts everywhere in my circuit. I didn't put earth because that's not really relevant to anything. And guess what? It worked after many tryings, but with errors, with many errors, until I start to figure it out. Here is another circuit that I find, and I compare. Actually, I was very lucky to find this one on YouTube. I find it was an Arab, some guy. He was speaking in a foreign language, Turkish or something, Arab from Turkmenistan, somewhere away, and he was explaining in his language, and I did watch him explain it in his language with a couple of English words here and there, that I could grab, and I copied his circuit, and I believe I did modify it myself as well to correct it, to adapt it to what I have here, until it worked, and it worked absolutely fine, absolutely gorgeously, and it helped me immensely to figure out my chip that I have. So this is his chip, the ADC0808, and I made a very distinctive and very important difference. This is all parallel. This is parallel in and parallel out, as you can see. You see this ins and outs? I'm not sure. Maybe he did mention this detail in his video, but it was on another language. But I'm mentioning in English here to be clear. So this is parallel in. You see all these in inputs here, and this is also parallel but outs. So this is the configuration of this chip, and it's very important. What I have, my 0832, is serial in and serial out, and it's a very different beast, very different. You send on one single fucking wire, you send all the data that you need, but in this case I believe I'm sending only the settings, the 0110 here, you see, so it's exactly 0110, and this code is sent here on this where on digital in, you see this, and also is clocked from the same clock, but is inversed, but it's coming from this line as well. You see, this clock is going to this chip, and here is inversed. When this is high, this is low, and when this is low, this chip is low, this chip is high, and is sending data, I believe, is receiving data. This actual code, this is what I could figure it out myself, and with the help of my friend, which he is very knowledgeable, way more knowledgeable than me, and much more older than me, more experienced as well, and he could deal with this configuration a bit more easier than me. He could understand it, but because of his certainty, he was very certain how everything should work, and that this circuit will work. That was the certain thing that he provided me with, his certainty. And I start to, and of course I believe him, and I start to believe that this circuit should work as he is saying, because he was very certain it should. And I start to understand actually this circuit little by little. But let's get back here. And let me present this. Yeah, this is a very little difference is having here, and is outputting a bit more differently because of this output pin 8 here is the first bit. So let's play it a little bit. This is very nice chip. I really like it. I had a problem on AliExpress. I put an order for this ADC0808, you see, 10 pieces of ADC0808 because I really like this chip. But check this out. Read here. Do you see here? They closed, the motherfuckers. They closed my my purchase. Why? They didn't give me any explanation why they closed it. They just closed it, and I didn't get my money back yet. But it is in a roll. Hopefully they will give me the money back. When you see here, I purchased it for almost $14, $13.88. But when I'm pressing this link here, it's opening here, and this is the exact same page. But check this out. They changed the motherfuckers. They changed the price. That's why they closed my order. The motherfuckers. I didn't like it at all, and yeah, they will suffer for this. And then I find another one, and this is today. I purchased them today, and it's the same chip. You see, times 10 pieces, the same ADC0808, and I paid a little bit more, but not that, it's not that much. And I hope these guys will not give me the same treatment to close the deal as the other ones. I hope. This is the first time when it's happening. They probably they changed their mind. Who knows? But this is very weird. This was very weird, and I wanted to show you this little detail as well. So let's see. It must be set on pin A. This ALIA, it was a single button that was switching to positive 5 volts, and then it wasn't to negative, it was to floating. So by setting this, keeping it all the time to positive is doing the job quite well. Here it is. The clock is very slow. Frequency 5 kilohertz. It's not slow. Oh yeah, I have some other stuff in the circuit that is working in the same time. It was working very fast. I was trying to figure out the output. How is correct? The correct output, at least here in this side. Oh, this is the original. You have to press this guy once, I believe. Yeah. And it should have been work. Yeah, like that. And keep it to positive. Let's see. Come on, update. Yeah, for some reason it's very slow. Shit. It shouldn't be this slow. It did work. It did work fine. But right now when I'm filming, of course, it's creating some delays and it's fucking with me. Shit. With some delay, but it was working when I was clicking. When I was changing this resistor here, it was updating itself extraordinarily quickly. And then I had to make some notes. 80. This should be a very interesting pattern. Yeah, this is wrong. This is a wrong pattern here. This is a good pattern. This is 80% of this. So this is the percentage, and these are the bits that they should be shown here. And I made this to actually figure it out, and I did figure it out. And this helped me immensely. This ADC0808 helped me immensely on understanding how it should work and how it should be linked and how it should be operated. This chip, because that's the problem. How to operate these chips. And my chip that I'm having, so this is the preliminary, the very first tests that I did, okay? So I will open this B version, I will make it full, and I will close this one, save, yeah, I did some changes there. And this is B, but what I did here, actually, I did change the original circuit that I had, you see here, I don't have this chip, this output shift register, I don't have it at all, 74164. And I imagined, and this is my doing, a lot of simulation here is my stuff that I did alone, without any help. So this 74, I wanted to adapt my integrated circuits that I have. So where are you? 74, this one. So you see, these flip-flops that I already have, and I have 20 of them. And I wanted to use my chips that I have them in my arsenal. Is all that I did here. I tried to adapt what I have. And I made an 8-bit shift register. I'm getting 8 outputs from all these flip-flops. So what I did here, I made the same circuit. Where are they? Is the circuit of this integrated circuit is the internal circuit of this one single chip, and I did try it with this chip by itself, and I'm getting a slight different result here in the output LEDs than when I'm making it with my chips, with my 7474. So there is some variations on whatever output register IC you are using. If you are using this 74164, which is 8-bit shift register, it will give you some results on the output. But if you are using 4, so if you are using 2 chips that are 4 bits shift register output, so instead of 1 you are using 2 of them to make 8 bits shift register, they will give you a slightly different output result. Very interesting. And if you are using this configuration that I'm using it here with the flip-flops, I am getting another very different configuration, slight deviations. But for some exceptional bits, I'm getting the same result whatever I'm using. If I'm using this chip or the 2 chips that are 4-bit shift register, or this whole entire line of flip-flops. So the common values are on 0. Not really. On some chip I get all of zeros without the first one as 1. But on 100% I get, this is common, 100%, and on 50%. On 50% here I get 1 and the rest are 0 on every chip. And on some, on I believe 77, I don't remember which, oh, I believe on 80% and 20%. As you can see, in 80 and 20%, I believe I get the same result on all. It is like a common, for everything. But there are some weird percentage values that they are not giving me the same bit configurations on all the output. These are the output driver. LED or LED display if you want, So what this circuit means, and let me play it, this will work absolutely fine. Unfortunately, the difference from this circuit and that ADC, let me open this again. I don't have to press, where are you? This 0808 is very, very nice, very, very nice chip. In the moment I'm switching the value of the potentiometer, it is auto-updating the bit values. I don't have to press any button. Originally, it had a starting button to kickstart the ADC, to start it. But that's it. You press it once and that's it. And after that, when you change the potentiometer, everything was automatically updating. But in my circuit that I'm having with this serial 0832, I have to press a button here. Every time so if I'm changing the value from the potentiometer here, so let's change it here, I have to press the button. Let's play it. So as you can see, it's not automatically updating. I have to press this button. And if I'm going to, let's say 20, it should be inverse. You will see in a second. Okay, so you see it's 1100, and it will be 0011, and here the same 0011 when I'm clicking this button. You see, back, and it changed. It inversed itself. Also, let's go to maximum, to 100%, and let's click. And everything is 111, and let's go to 0%, and is all off, but only the first one is on. Exactly as in my list that I'm having here, and everything is repeating exactly as I'm having here. But I have a very interesting problem. Sometimes is giving me some errors, and I get these errors. You see these capacitors that I put here, they are not in the original circuit, and I had to include them here because without them it didn't work at all, the circuit. So this is the overview. So this is timing. Here is timing circuit. This is holding circuit. This is the actual ADC. This is the potentiometer, and this is setting circuit. This is a setting circuit, and this is the output and driver, and these are the output LEDs. And okay, so I didn't write down anything, but I will discuss and I will explain everything very quickly. So this is timing circuit, and what I did here, so let me do it again. So this timing, actually let me stop it because this is running, consuming too much power. So this timing circuit here, it is timing both this chip and this chip, and yeah, only these two, but not here. So not here not. It's not timing anything. It is, where is the line? This is the line. It is, you see the timing, this is the output of the timer here, exactly on pin 3 here, in this node. And it's going here to this chip, and this line is going to that chip. And also a single line here that is going to one pin of this NAND gate. But this is a whole, this is a different beast, a different circuit that is doing something quite important and quite smart. It's very smart how he made it work here. But this is not activating, it's not pulsing anything excepting that pin, but it's not transmitting anything after it. So this is just sitting, waiting, while one of its pin is pulsing, from the timer. So the timer is basically powering this chip, and like I said, only this chip and only that chip. That's it. And so this is only the circuit for a timer. That's it. And this ADC, from what I understand, this ADC, it needs a code. And when this code, and this is the code here, 0110, and when this code is at a certain timing pulse, this part I didn't understood it correctly or fully. This part I'm not very sure what it's doing, and I couldn't really test it enough to figure it out. So at a certain, when this pulse is like this, the clock is 1. This chip that I'm having here is bursting all these 4 bits at once, and this is acknowledging it, saying yes, I'm getting that setting number there from there, and yes, I will transmit the value that I'm reading on this potentiometer. I will transmit it on my output here. But when the clock is going down, like that, from the timer here, from this timer, probably this chip is still transmitting something, but this is a reading that is down, this is negative, and is not transmitting anything further, or something. It is not transmitting, I'm not sure exactly how is the mechanism, but it's my impression that is sending all 4 together in one single pulse, when only it is positive like that. It's my impression. Or it might be, is separating them like that. 2 bits and 2 bits, so 2 and 2. So first 0, 1 on one pulse, and when it's down, or the next pulse, the next high pulse, will transmit the other 2 bits. And yeah, I'm not very, very sure how is the mechanics of it, because it's weird. Why I'm saying this, why I'm explaining all this stuff, because sometimes it's depending on this. Sometimes I'm getting this value, the value is read correctly, but sometimes it's not. Let me press multiple times until I will get an error, hopefully. and it's hard to get that error right now because it is quite domesticated right now. Come on, give me the error. Come on, motherfucker. I don't know how to create that error. Oh, I believe I know. I think I know. Let me take out that capacitor link from there, and this should give us. Yeah, there it is. There is the error, and everything is on. You see, actually everything is off, is negative here, and is permitting these LEDs to stay on all the time. So that capacitor is actually helping a ton for the correct when I'm clicking once to actually transmit correctly every time. Let me window. So when I'm getting that error is because the timing and the code that is transmitting from this chip are not on the same value or on the same register or something. This chip is doing something dubiously, very, very dubious chip. Sometimes it's reading, sometimes it's not reading this input pin. And the solution, let me actually open this, its datasheet, and I hope I will get very quickly to some data, I believe. 34, 32, this is the ones that I need here. So this is the MOX the addressing, and it's very, very weird. Very weird. I couldn't figure it out by myself. My friend from England, he figured it out for me. He managed to understand it way more better than I did. So he realized these are only these 2 bits, or at least it needs 2 bits to be accessed in a corresponding order. 1 to be 0 and 1 to be 1, or 1 to be 1 and the other bit to be 1. And it's this address that we have here. And that's from datasheet. And that's the code that is transmitting. But we didn't figure it out when or how it's transmitting it, or how this chip is reading that code, in what time sequence is reading it. If it's only 1 pulse, if it's 2 pulses or 4 pulses, I have no idea. So we had to guess a lot how to make it. And I had to guess a lot because I did this big circuit that I'm having here. I did it by myself, and I tried a lot of permutation until I figured it out. And I'm not sure for what chip, but probably for all the chips at once. Its clock frequency is having a minimum. Let me do it like this. So it's minimum kilohertz. So it's minimum here. You see, minimum is 10 kilohertz, and maximum is having 400 kilohertz. So if I'm clocking this chip with 20 kilohertz, it should work. But here in my circuit that I'm having, I'm not powering it with that frequency at all. This is way more slower clocking frequency that I'm having here in this circuit that I'm having. I'm not sure how slow it is actually using this 10 nano capacitor. It may be too slow. So this is his explanation why I get this erroneous, you know, when effect when I'm clicking. Sometimes when I'm clicking, I'm getting the error, and sometimes when I'm clicking, everything is working fine. And that's very weird, at least here in Proteus, where everything should work at a lower frequency. If I'm increasing the frequency too much, Proteus will shit itself, and it will give me errors. It's not made for very fast frequency, but it is working absolutely fine with lower frequency. And it's a rule that I learned it in time and using this software. And I learned it, you know, by using it. So it's my experience that I'm talking from. So this is one important thing: the timing and the code, the clocking and the code to this chip is very, very important. Then we played around, and I told him, well, I don't have this 4093 chip at all, and I was very. This is also a very new thing for me, of making a clock from an NAND gate. I'm not used to it. At least I'm doing it practically, you know. And what I did practically, I use the 555 most of the times. But there are other ways of clocking, and this is very interesting modality. And I tried it with what I have here, with 7400 and 741 in the idea, in the hope it will work, and it didn't work at all. And let me actually show you. So you see, when I'm activating this, this is working, but this is not having any switch, and it's not working at all. It's just, and I tried everything. I really tried everything. I tried to blink it. Yeah, it didn't work. But this worked fine. And this is the finding my friend from UK, from United Kingdom. He find this solution with a NOT gate. With a NOT gate. It's a very, very interesting solution. Let me play it actually for you. So you see, when I'm switching, it's having a very weird way of playing actually. Do you see this gray squares? This two, it means floating. When it's gray, it means floating. When it's blue is negative, is 0 volts. When it's red is positive, or 5 volts. So, but this is floating, and sometimes it's getting positive. Very weird configuration, but it's working. I don't care why it's working. I care if it's working, and it is working. And so we have here two ways of oscillating this thing. 7414 chip. I do have them in my list of chips. You see, 7414. I have 10 of them. I can use this particular clock configuration, clock circuit. So I can change all this clock that I'm having here with that simpler one with the NOT gate. That's very important, at least for me, because I want to make it with the components that I have. That's the goal of this, what I'm trying to do here. So this was number the B1, and now let's open the C1. And what I did here, I copied the same circuit that I have there, but I only change this, like I said, this clocking circuit that I'm having with the NOT gate. This is I'm also using the chips that I'm having, all the flip-flops, all these flip-flops, 74, 74, I do have them. The 7414, I do have them. This is the button that is resetting this circuit. And I do have 74194, I think. Let me see. 194, yeah, I have 10 of them. And also, I could change, because in the original circuit, one single chip is having 2 NAND gates, one single chip. So that chip that was here, it was used only for switching, on and off. And I replace it with what I have here. And it is functioning absolutely perfectly, as with the other one. And it's on 10%. Yeah, you see? I might, yeah, the clocking is quite slow. Yeah, because I use here 10 microfarads, probably for debugging, for debugging purposes. You can see, pay attention to the output. You will see them actually moving from right to left, one by one. You will see when I'm clicking the button. You see, and how the bits are moving. And because I use this slow capacitor here to slow down the output very much, it's slowed a lot right now. I could figure it out. I could figure out what this circuit is doing here. This is the whole circuit. If I'm not connecting this circuit, it will pass all this data stream. It will pass, and it'll be 000 or 1111 everything. It will get into an error, and it will not stop here at the, the correct sequence will not be hold it in place. That's all this circuit is doing here, and it's perfectly fine with a simple 7400 and not using the Schmidt trigger one. It's absolutely okay. And also another 7474 as the other one, another flip-flop here. And this is getting the signal. Actually, you can see the reset signal is getting it from this line now. Yeah, when I'm clicking this reset button here, is resetting all these flip-flops. This flip-flop is reset, and all these output reset pins are flip-flops. All these reset flip-flops pins are resetted. So the entire driver is reset when I'm clicking this button here. And this line is coming from yeah, the last bit. You see, this is the last bit here from this output, from the last flip-flop, and the last bit, which is this LED here, this guy here. And when this last bit is used, it will send the same signal. It will be sent here to this flip-flop, and because this is flipping all the time, this will count very, very fast. When the NOT queue from this flip-flop will be activated, it will catch one activation from the timer that I'm having on this pin, and it will clock only once all the output, and including this guy, and switch it to off. It's it will reset everything pretty much, and it will start a new sequence or something. It's very clever. I didn't figure it out too much in depth, but I figured it out. That is a holding circuit. This is what is doing here. That's all the thing that I could manage to figure it out by myself. And this is the circuit that I wanted to present to you, how I started it, how I got some help about it, and how I converted it, because this was the utmost important thing, how to convert it using my chips that I'm having. But I'm having some something else to add, that I already made a purchase of this 0808 ADC, which is a parallel ADC, but also this 4093. The 4093 is the NAND gate that was here in the start to actually this guy 4093. Oh, it's a bit more simpler, I believe, with it in the circuit. And this 74164, yeah, it's 8-bit. You see, where are you? 164, 74164. I don't have this chip at all, and it appears to be very interesting to have it. I have 2 4-bits. Let me actually. Okay, so the 4-bit chip that I was having all the time, and I didn't realize it, was the 74194, and this 74194, I can use 2 of them here on the output. So pretty much, so this 74194 is first used as the setting coder to create the code and transmit it to the ADC. But here on the output, I can use 2 times 74194, like that, and it will act as a single 74164 4-bit, and this is 8-bit. This is 8-bit, and like that. You see, and 2 times 4-bit equal 8-bit. Pretty much that's so 2 chips of 4 bits will equivalent one 8-bit output chip that I'm having here. That's the idea, and I tested it, and it worked. With 2 74194. I have to search it. Let me search. I believe I'm having it somewhere in A, probably. because here I made, yeah, I believe, yes, this is it. You see, 74194, and it did work. It did work absolutely fine with this two of them. You see, but it's a bit more complicated to wire it. But it's okay. It's quite fine. It's quite okay. So pretty much, I believe I did explain everything to that here, and I hope you like it. This is all that I did here. I converted this circuit that I'm having here with their chips that they had there. I converted into a circuit with my chips that I'm having. That's all that I did here, and it's very important to be able to convert from what you see to what you have. That's very, very important, and I hope you learned the lesson here with me, and that's it for this part, because this is an extensive and very, very complicated, a bit too complicated subject, and yeah, I hope you like it, and also leave a like, say thanks, and yeah, see you later when I will build this circuit on the breadboard. Well, one second. Another circuit that I'm having, I tried with Arduino. An old, yeah. So this, let me check if this is running. Okay, good. So this is the next step, but I couldn't figure it out. Here I tried to make another timing circuit using an op-amp, LM358, and even UA741. I tried it, and it worked with both of them. But from what I understand, my good friend from England, from UK, he suggested me not to use an op-amp because it's very slow, he said. So he told me to use, or to stick to this not Schmidt trigger not oscillator that I'm having here, with this one or the NAND one, whatever I'm but it's interesting that I can do it with an op-amp as well. We will see in reality how it will work with an op-amp. I'm very curious how it will work, but it is working as an oscillator like this as well. All right, and the rest of the circuit is quite the same as the thing that I'm having here. The only thing that I could manage to replace was this code circuit that I'm having on the top with this Arduino board, in which I've already loaded a hex file. I made it on Arduino. Let me Arduino test. This is the program. It's really not that big. And as you can see, I'm setting up, so from the setup, I'm setting up this two pins 13 and 12 as output. So this is the 13 and 12. I was trying something on 12. My idea with Arduino was to clock this chip and clocking it from the Arduino itself, and so timing the Arduino code and the ADC in the same time. But I don't really understand the clocking mechanism that this ADC is using internally. I really don't get it yet. So that's what I was trying to do. Then to send the data, the 0110, to its digital input here, and also so using 3 pins from this Arduino, and also making the hold that this circuit, the whole circuit that I'm having here, this thing to hold the data from. So this will be managed from 3 pins, pin 11, 12, and 13. But I had a very, very big problem. I couldn't really make it work on pin 11 and 12, and I'm stuck. For the moment, I'm stuck at pin 13, which you can see it here is linked already and is working absolutely fine on pin 13. And what is doing exactly? It is sending a burst, a single byte with 4 bits in it. So the byte is 0110. This is the byte, and the bits are these numbers 0, 1. So this is bit 1, bit 2. So this is bit 1, bit 2, bit 3, and bit 4. Okay, so it's exactly as that circuit, as this circuit that I'm having here. You know, it's exactly like this, but replaced by an Arduino or by a PIC microcontroller. It could be made with that as well. It's all that is doing here. I made a variable, which is in this case is used. The idea that I'm using it is used as a constant, not as a variable. But you can vary it. You can change it into something else whenever you want. But in this particular case, this x is not a variable, is more as a constant. And I'm sending this x byte constant, I'm sending it on pin, you see digital write 13. And on pin 13, transmit this burst of information, 0110. And I also transmit this low or a 0 at the end. Without this line, it didn't work at all. And for some reason, I have to include it here. I can put low or 0, whatever I want, and it will work absolutely fine, and it is working like this. Make abstraction of this reset, as you can see, is commented out, is not used here, because I was trying the other pins. If you remember that I explained earlier, and is not functioning, is not working. The ADC doesn't like the clocking and the code in the same loop. I have no idea why. And I write to the guys on the forums on Arduino, and they couldn't tell me anything. They couldn't comment about it at all. They didn't want to complicate themselves, probably, because this is an old. They told me this is an old chip, and I should look on newer chips. And probably they are right, but it's what I have, and I want to use it. And it's a very interesting subject of learning about ADCs in general, and electronics in general, and how to hook them up. So this is all that I managed to do with Arduino. Unfortunately, it's not doing that much. So let me play this program for you. And I have a counter that is counting what is transmitting here. And as you can see, it's very, very fast. It's transmitting a lot of data here. But the timer is very slow. It's very slow compared with that data that is transmitting all the time. That burst of 0110. But here is very, very slow, the counter. And when I don't have to press it. Yeah, here probably. Yeah, you see, and it doesn't all the time get on the right bit. Sometimes I'm catching the, yeah, this is good. I catch the bit here, but sometimes it's not catching it. And if I'm doing 80%, let's say, yeah, let's say 80%, it should be something like 1100 1100. So let's see if I will catch it. It's still remembering that 50%. It's having like an internal memory, and then you see now is actually catching that 80% that is there. And very interesting how this is working. I didn't completely understood it, but I did get something from it, you know. And if I'm pressing it again, and now if I'm doing it at 20%, there it is, it should be inverse. It should be 0011. And when I'm pressing, it will still remember the last one. So this is not correct. This is still 80%, and this is the correct one. This is 20%. So 0011. You see, and it's very interesting. It's very interesting. Although it's not functioning absolutely perfectly or automatically, what I really wished for, and that's what I want to do with the Arduino, is to make everything work without me pressing that button. When I'm changing this potentiometer here, to auto-update itself without me pushing the button. That's the idea that I want to. Final circuit, I hope to realize it. I doubt I will, but so far so good, you know. And yeah, let me close this one. Save, not ready. And that's it for this project. Really, thank you very much that you had the patience and you listened and you watched all this long movie, unfortunately. And I hope you like it. And leave a like. Don't be a motherfucker. And leave a like. And see you next time when I will actually build it on the breadboard. And most probably I will build this circuit that I'm having here with the chips that this converted circuit that I'm having here, that I already have all these chips in my arsenal already. Alright, thank you very much. Goodbye from Romania, from our favorite artist electronist, Mr. Q12. Bye bye. See you later.